It's Teresa. Good morning, Teresa. Nice to have you there. Whoops, but I'm writing at the wrong spot. There it is. Super. Teresa, what do you do to stay sane? What are you doing when you're going crazy at home since the middle of December? Allie, good morning. Same question to you. Allie, what do you do to stay sane? Like for me, I go for walks in the woods or I play with the cat sometimes. Read books, go on walks though it's cold. Yeah, good. Yeah, book reading is good too, Teresa. Yeah. Yeah, I've done some of that in the last couple of months, read a couple good books. What about Allie? What do you do, Allie, to stay sane in these crazy times? Sewing's cool. Most of you are not sane. Oh, yeah, unfortunate. Yeah, I believe it. It's not an easy time. Not an easy time. Yeah, if there's anything us teachers can do, let us know. Um, yeah, and if there's anything I can do, especially with our physics class, let me know. Morning, Zach. Zach, same question to you. What do you do to keep sane in these crazy times when you feel stressed out? What do you do at home there? The reason I asked this too is because, frankly, some of us teachers have gotten together and we know it's hard for us in these times trying to keep everything together. So we know it's also really hard for you folks as well. They're trying to just do everything on your own at home. I'm sure it's hard to keep focused and motivated and to keep happy. It's hard to be happy when you're at home all the time and not being able to interact with friends and stuff, at least not so much in person. Is there anything you do, Zach, to help keep yourself sane in these times? Maybe you're still writing. And I'm missing Anne Sophie today. That's a bummer. But maybe she'll show up. And while Zach is thinking, I'm going to get a marker ready. And we'll start up with a little physics today. No, nothing else. Okay. If there's anything we can do to support you guys as teachers, let us know. We'd like our students to come back healthy and relatively sane when we actually get back someday in the classroom. Hopefully, as teachers as well. Okay, we're going to continue with sound and with waves here today. We mentioned last time some stuff about, pardon me, we mentioned some stuff last time about animals that can hear infrasonic and ultrasonic sound, which is pretty neat. I thought I'd list for you also some uses of ultrasonic sound. I bet you know at least one of them. What do they use ultrasonic sound for? There's several answers, but probably all of you know one, at least. What do they use ultrasonic sound for? Are you still with me? Yes, yes, no, no. Maybe nobody knows. The German word is Ultraschall. Ultraschall. No? Going once? Going twice? You guys are kind of quiet today. Echolocation. Yes, in a sense, Ellie. Okay, they use ultrasound. It echoes back and forth in a mother to look at the baby. So ultrasound for examining the baby in a mother, or other tissue as well. For instance, years ago, I had a problem with my knee, and the guy used an ultrasonic sound to look at the cartilage and stuff in my knee. Okay, ultrasonic or ultrasound. Detecting objects and measures. Yeah, I'm reading what you wrote. Detecting objects and measures. Yeah, we don't really use that, but animals use that, of course. So I'll list that. Okay, we kind of said that last time. So bats, um, dolphins use to find their prey, right? Fish or flies in the case of bats. Here's a cool thing, by the way. Here's a school of fish. Did I already tell you this? If I want to tell another dolphin about this, I can memorize the picture from my echolocation picture, and I can go to another dolphin and actually go, ah, and I can send them through the ultrasound that I give the other dolphin a picture of that location, including the rocks or whatever in that spot to help them know where the fish are. Now, is that cool or what? So they can send an ultrasonic picture to another dolphin. Kind of fascinating stuff. Okay, well, so I meant more like human uses, okay? So ultrasound for examinations. And another is it's used as a cleaner. Cleaning, for example, jewelry. Jewelry, if I could spell that right. Yeah, you can buy ultrasonic cleaners and put your metal watch bands and stuff in there and turn it on. And it goes, and you can't really hear it very well, but it's cleaning very, very effectively. And AP chemistry will talk about this. It's used for plating, like putting a bit of metal on the outer part of your key, for example. If I have a key, they're often plated. So for metal plating. And another use, oh man, I'm sorry, is it just gone out of my head? I know the odd use. One is to make mayonnaise, but that's not really all that important. Let me think. So it's examinations, cleaners, metal plating. Oh yeah, so it's to reduce coal burning power plant emissions. I've got a great video, which I don't have digitally because I can't send it to you. It's pretty old. But you probably know something about this already. Okay, if you burn coal, here's your emissions. If you burn coal, you get a lot of soot in the air. Bump, 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 nasty stuff. And what they do is they send ultraviolet waves through this. And what they do is they cause the emissions, the little bits of soot, to join together and fall down to the bottom. Oh man, my drawing today is really bad. Sorry. So emissions join. We can say they clump up, if you like that expression. Clump and fall to the ground. So it gets it out of the air. So let's say coal emissions. And this wave would be the ultrasonic wave. I'll abbreviate that. Ultrasonic wave they send in to do that. So ultrasonic is pretty cool stuff. Yeah, exactly. Okay, good. Very, very well. I know less uses of infrasonic, to be honest. I don't, other than by animals. Okay. What else? We talked about the sorry, my studio is pretty small here. We talked about the comparison of sound and light, and of course, sound is a lot slower, light's a lot faster. We talked about the transmitting of sound. We got that. Okay, sorry. I know where I want to go, and I think we're there now. Man, I don't have this with me. How am I going to do this? I could do it like this, I guess. You ever notice how when I hit certain things, no matter how often I hit them, they give the same sound? See if I can do the same with the marker. Ow. That sound is called the natural frequency of the object. So natural frequency is the sound an object gives off when it's struck. Another example, so I used my whiteboard. But what's a really good example from music class? Music class, something that gives off the same frequency every time I strike it. So the sound or frequency an object gives off when struck. Something in music class that gives off the same frequency over and over and over. Now, I could say a drum, but that's kind of like my whiteboard. Thank you, Ellie. A tuning fork. So one reason we use tuning forks to tune things is bang, bang, bang. They always give off the same sound. So that's their natural frequency. Well, it turns out even big objects have this, and that's where I'm going with this. I'm going to send you a video about this, but it can be a good or bad thing to have a natural frequency, so to speak. Okay, let's talk about, I can't really do that. So let's not talk about that. Let's talk about resonance. Let's go right to this. Resonance. It's the same word in German, Resonanz. This is something that, ooh, and I can get something for this. Okay, hold on. Resonance is when one object matches the natural frequency of a second object. The second object vibrates intensely or resonates. And while you're writing, I'm going to go get something to help show you this. If I can get out of my studio and not kill myself. Okay, hold on. Be right back. I'm back. So I bet you've seen this before, okay? Probably in a video, or if you're lucky, you've seen it live. I've never seen it live. I've only seen it in a video. But I got something, and it's a wine glass, and it has a really clear natural frequency, doesn't it? No matter how many times I hit it, I can make it ring with its natural frequency. Well, what could a good singer do, like a good soprano, or this might even be an alto singer? What could they do with this glass? A really good, powerful singer. And while you're thinking, I'm going to write down that as an example. I'm going to set this down carefully. If I break it, I'll be in a lot of trouble. What could a singer do? Sing the same note and shatter the glass. Yes, exactly, Ellie. So here we go. As an example, then, an example of resonance is, here's my glass. And yes, if a singer, oh man, I'll try and make this person reasonable. If this singer, if she sends out this same pitch, then suddenly this thing can absorb a lot of that and really start to resonate. So, example. So singer matches the frequency, the natural frequency of a wine glass and it resonates. Now, the way to recognize resonance, I'm going to try and do that so I can do it. Okay, I'm gonna cover it up. Here we go. Didn't work. I'm not that good. If I get a person, even without breaking it, they can hit it, and when they stop singing, you'll hear it making the same sound. It's cool, even without going far enough to break it. But my point is, okay, is the way I can recognize resonance. So you can recognize resonance by the greater amplitude of the vibrations. And I tried to show that here, okay? So my point is, resonance transfers a lot of energy from the first object, the singer, to the second object, in this case, the glass. So in resonance, a lot of energy is transferred. This can be a good or bad thing. Let's do another example. Do any of you have a little brother or sister? While you're thinking about that, here's your little brother or sister on a swing. Hey, that's one of my better pictures. And here's you. You got a little brother. Okay, let's see if you did this when he was younger, Ellie. Did you ever have to push him? So it'd be like this. Here you are. Here's Ellie. And she's going to push him. And he's all excited because, of course, the swing goes higher and higher. But here's the deal, right? Watch this. I've got to match that swing, don't I? Right? If I want to get that kid going higher, right? Ellie's little brother going higher, I got to match that natural frequency of the swing. Well, let's say Ellie's going to do a little experiment and she decides not to match the natural frequency. So here, I'm sorry to give you a hard time, Ellie. Let's say Ellie, so she's going to just do randomly. So here we go. Here's the little brother on the swing. Ready? Huh? 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 What's the little brother going to do? Oh, hey! It's not going to work very well, is it? So if you match it exactly, the natural frequency of the swing, you can make essentially a case of resonance with the swing. That's what you do when you match it. If you push the kid randomly, it's going to be just a big unhappy mess. And the kid's not going to get nice and high. Maybe that's what the little brother wants to do, right? Thanks, Ellie. I bet he would be annoyed too. Okay, so if Ellie was feeling much happier, then we would say, so if she matches the natural frequency, I'm going to abbreviate that, nat freq of the swing, then swing resonates. And in terms of physics, that enables Ellie to give much more energy to this swing. So, of course, it goes higher. So, more energy is transferred. That's the case with resonance. It transfers more energy. More energy is transferred. I know I'm running out of board. I hope you can still see it. Let's see if you can. I'll read that in case you can't see it very well. So here we go. If she matches the natural frequency of the swing resonates, so more energy is transferred, resonates, and goes higher, obviously. And I think the going higher, of course, is how we see physically the resonance of the swing. We think of a resonance as a vibration, but in this case, the vibration's more like the pendulum, right? The swing moving back and forth higher and higher. But it's the same idea, right? Okay, so now there's two cases of resonance. Here's another one. This one's about my dad, okay? So my dad had a car, so I'll say a car owner notices a rattle in the car when car goes exactly 60 kilometers per hour. Can you guess what's happening? So I'm below 60. Here's the car. Suddenly I get close to 60. Now I get beyond 60. So at 60, can you guess what's happening in the car? It's not something owners like. And it doesn't happen in every car, but it happened in my dad's car. That's why I know about this. Can you guess what's happening? What is the rattle? What's the rattle due to? What do you suppose? What's the rattle due to? There's probably two answers, but what could the rattle be due to? Put that down here now so I can spread out a leg a little bit. All right, good. Okay, Ellie, you're on the right track, so to speak. It has to do with the motor. So the motor sends out, think of the motor, so there's pistons and stuff working. It's sending out a vibration. So the rattle's due to the motor's vibration matching, if I could spell matching the of a car part. So somebody else maybe help us out here. So the rattle's due to a motor's vibration matching the heh of the car part. So here's the car. Maybe here's the part right here that rattles. That's not much of a picture, okay, because I can't really ride the motor in there. But the motor's going to match the you got. Okay, so the natural frequency, right? Of the car part. And so the car part accepts that energy and rattles. Now, you might have heard this on the S-Bahn. I know I have. You ever been in the S-Bahn when the window's open and then the S-Bahn hits a certain speed and suddenly you hear that window start going, and it's really annoying, and then you shut the window because it's bothering you so much. Well, that's probably resonating, that window. Not every window does, but I've noticed some in the S-Bahn do. And it could be either due to the motor or it could be due to the wind on the outside pushing back and forth on the window of the S-Bahn. You know what I'm saying? So resonance can be a good thing or a bad thing, depending. Okay, I'm going to send you a video, a short video that will have some resonance in it, and I think you'll see in this case it's not a very good thing. Maybe I want to tell you something about that ahead of time. Maybe I don't, but you might have seen before anyway. Okay. That we've more or less done. Oh, by the way, if you're tuning your radio in the car, you're more or less doing the same thing. You're tuning your radio until it matches the frequency of some radio stations that's being sent out. And then once it matches it, then it gets nice and loud and you can hear it, right? So when you tune it, you're matching the object essentially inside your radio to the waves sent out by the radio stations. Unless you have internet radio, in which case, never mind. Right, okay, let's go on, and I want to show you something and talk about something, and it's something you both have two of, and there's a lot of physics in what you've got. We'll start this today, and I don't know, we can't really do it all. In fact, I gotta have the whole board here, so I better erase this. You ready? Oh, this is so old, but it's kind of good in a way. Ta-da! I'm going to go through this with you. Is there any way I can make that stay? Nice. What if I do this? Doesn't work. Maybe I can do it down here. Yeah, that's not bad. Let's see if you can see it. No, it's really glary. You can't see a damn thing. All right, let's put it over here. Okay. I want to talk to you about the physics of the ear, because a lot of the concepts you and I have talked about have to do with your own two ears. Okay? All right, so I think I'll write here and then over here, and I'll have to lean way over. I know that. So let's talk about ear physics. You can draw this if you want. I'm going to point out some parts of the ear. I know it's not easy to draw, and you can also just find some sort of diagram on the internet if you want, but I'll kind of point it out. Okay, for starters, we've got compressional waves. So let's let these little lines coming in, see those? Let's let those be the compressions, right? So ear physics. So sound is a compressional wave. Well, why is the ear so big? Why is the ear so big? What's happening? Why not? I mean, look at the little tube. Why isn't it just like that big? Why do we have a really big ear? Why are our ears so big? Why are our ears so big? There you go. So, um, exactly, Ali. So the ears are big to capture sound. You ever seen the ears on a deer? They're huge compared to the size of the deer. They're a really big feature. Why? Because deer need to hear well. They want to hear predators, right? They want to hear if somebody's going to sneak up on them and try and eat them. So a lot of animals have big ears for that reason, okay, to capture the sound. Okay, here comes the sound. Ready? Okay, now it's going to go in this part, and that part is called the ear canal. You're probably familiar with that. So the ear canal, here's something you may not have known. Because of its shape, the ear canal amplifies some sounds for us. Isn't that kind of cool? I want to say it's like the 5 to 6,000 hertz sounds. So ear canal's shape amplifies some high frequency sounds. All right, then, what's at the end of the ear canal? I know you can't read all this, okay? But you know it probably, right? So the sound comes in here, it goes in the ear canal, and what's at the end of the ear canal? If you stuck your finger way in there, you can touch it, but don't do that. Besides, your finger's too big. What's at the end of the ear canal? What am I pointing at? Exactly. Teresa and Zach, you out there? Please type in. I like to have everybody participating. I know you haven't fallen asleep. So the eardrum, the cool thing is it doesn't resonate. It undergoes what's called a forced vibration. So the eardrum is forced to vibrate at any frequency that hits it. So it's not vibrating at its natural frequency, it's vibrating at a lot of different frequencies. So is forced to vibrate at many different frequencies. Okay, thanks, Teresa. Okay, I understand, Zach. Okay, just try and chime in. That way I know you're there. Okay, so the sound comes in, it's the high sounds are amplified. Then I hit the eardrum, and the eardrum is a change in medium. Let me ask Teresa and Zach, have we had the word medium before with waves? I think we did. What was a medium? Because I got to use that word in the next few minutes. What's a medium when we're talking about waves? I want to make sure we know that word. Hmm. Um, yeah, okay, good. Thank you. Thank you, Zach. So it's whatever the sound is passing through. So a medium could be air, a medium could be um, the ground, if the sound's going through the ground. The medium could be water if you're underwater. And in this case, the medium changes to the eardrum. So the eardrum is forced to vibrate at many different frequencies. So now we're going to change mediums again. The eardrum is connected to three little tiny bones. And the three tiny bones are levers. Levers. They're called the hammer, the anvil, and the stirrup. Okay, so eardrum connects to a new medium, and the medium is bone. So the vibration is passed on to these bones. So the hammer, anvil, you might know this from elementary even, and stirrup are levers. You might remember a lever was a simple machine, and simple machines increase force. That increase the force, or what we would say is the loudness of the sound. You ready? Here's the cool thing. They amplify the sound about 9 times. So if you think about it, what you hear is actually about 9 times softer. The bones amplify that sound because of the shape of the bones. Is that cool or what? So what you actually hear is softer than you think. So sound is amplified, right? Means to make bigger, amplified 9 times by these bones. Whoa, that's cool. Your ears are amazing, really amazing things. But the most amazing is yet to come. We'll see if we get that far. So we're going to change medium again in a second. Here, I'm going to make a little room. Let me read the red off in case you are catching up here. So the eardrum connects the new medium bone, and it's the hammer, anvil, and stirrup are levers that increase the force or loudness. So sound is amplified by about 9 times by these bones. In the same way that a hammer, because of its shape, bam, bam, amplifies the force that hits the nail. Like you wouldn't turn a hammer around and hit it with the handle. That'd be stupid. So if you have it shaped the right way and hit the hammer, you have a lot more force with using a hammer. Well, all three of these shapes do that. All three of these shapes increase the force. That's why it's increased totally by 9 times. So pretty cool. Since we have just 1 minute, I think I'm going to tell you what's going on, but we're going to draw the rest of it next time. Okay, here's what's going on. All right, the sound then goes from the stirrup and it hits this big bag, and it looks like a snail. The snail is called the cochlea, and the snail cochlea is full of water. It's called ear fluid. So we're going to change medium again. It's going to go through the fluid in your inner ear. You probably knew you had inner ear fluid. I bet you did. Inside the cochlea, we have little tiny cool things, and that's what we're going to talk about next time. Okay? So that's it. Until next time, and I'm going to send you a short video to watch about a use of resonance or an application, not something good, but an application of resonance, which I think you'll like. And that's it. I'll see you later in the week. I'm also going to send you a worksheet to work a couple problems of Doppler. I meant to do it last week and I just couldn't find it, but I finally found it. So I'll send that today. I'm going to have you do like 4 problems, not a lot. And then I'll give you a reasonable due date for some of those, okay? To keep you up on your practice. So we'll practice Doppler and then we'll finish off the story of your hearing and the physics of the ear next time. Good. Thanks very much for being here. And I'll put this in the live stream if you want to refer to something. And we'll see you guys soon. Stay healthy and stay sane. Please try.